Okay, take two. Chemistry was all about changes in matter. Physics is similar in that we're still going to talk about matter. Okay, so let me just write this down here. Chem is about changes in matter. Remember what our matter is? Matter is our our stuff. It's anything that has a volume. That's volume, actually. Taking up space is a volume, and has mass. What we're going to talk about in physics is energy and matter and how they're related, which is why my first topic today is to discuss energy. If it's not matter, it's probably energy. Okay. Like, let me give you some examples. The desk you're sitting in, it is matter. It's a thing, right? But is fire matter? No, fire is probably best described as like a form of energy, right? Light. Is light filling this room up? Yeah, light takes up space, right? Like the light is filling this room, but like you can't really weigh light. So light's a form of energy. So this is why I teach these classes in this order, is that now that we've talked about the stuff that we're working with, now we have to talk about how it moves, how it does things. Does that make sense? Because let's say we had a universe full of matter, and it just sat there doing nothing. This is really boring. Right? Energy gets you moving, and you get what I'm saying here? So physics is all about now how we take the stuff we have and we put it into motion. We do stuff with it, okay? So in general, what we're trying to do is figure out how the universe behaves. Why do the planets move? Why does gravity cause things to fall? How do magnets work? When I throw something, why does it go that direction? Right? That's what physics tries to do. I need to give you guys a bit of a warning here. Physics is highly mathematical. Okay? You need to have some decent math skills. Okay? We're going to work on them together in class, but you're going to want a calculator basically starting tomorrow and for the rest of the unit. You're going to want a calculator. You can use your phone, but if I could give some advice, the calculator on your phone is probably not advanced enough to like do calculations quickly. It'll work, but like it's very crude. Like it struggles to do like multi-step calculations all at once. You probably want to get like your math calculator. Okay, but if you want to use your phone calculator, go ahead. Physics, although it's very math-based, so I mentioned that, physics is highly correlated with math. There's also a lot of overlap with chemistry and astronomy. And I know you guys haven't done a lot with astronomy, but like basically physicists, they like to spend a lot of time figuring out like what's going on in outer space. Stephen Hawking, you ever heard of him? He was the guy in the wheelchair. He died recently, yeah. He was a cosmologist, okay? Not a cosmetologist, a cosmologist. He studied black holes, which is like really challenging to do because we can't physically go to a black hole and like test it. You have to like observe it and do predictions on it from far, far away. And so like a lot of physicists, they're working in like theoretical realms. They can't actually go out and try things. They're like making up math equations for how they think it works. So that's actually what I want to describe here. There's actually two branches of physics. There's what's known as the classical physics. And we're going to start there. Classical physics is also known as Newtonian physics, and it basically describes everyday life stuff. Like, why does stuff fall? When I push things, how does that work? How does fire work? How does light work? Okay, that's like everyday life stuff. Around the year 1900, physicists were they were a little bit cocky, I guess. One of them even published a paper that said, "We've figured out everything there is to figure out." They're like, "We know it all, guys. I can predict why the planets move the way they do. I can predict how light behaves the way it does." And then all of a sudden, quantum physics came around, which is the modern physics. And maybe you've heard of quantum physics before. There's some cool stuff in there. And we discovered that the laws for things that are very large and very small, they behave very weird. If you'd like, because I mean, I love physics. It's my main thing I teach here. I could go into so much detail on this. But like, there are some really cool theories in physics on things like many worlds, alternate universes, teleportation. All of these things are not just science fiction. We actually believe them to be true, and physicists are currently working on trying to understand them better. Maybe you've heard of things like Schrodinger's cat. Have you ever heard of that analogy of it being both dead and alive at the same time? That's modern physics, and it's very strange and very weird, and it's currently being worked on. And yeah, people like Schrodinger or Einstein worked on that. Okay, we're gonna get there. We cover this in Physics 30. So if you find the really weird stuff like teleportation and alternate universes, if you want to talk about that, I can talk with you about it, obviously, right? But you got to take Physics 30. We got to get to that point. We're going to focus on like everyday life stuff. Sound good? So we're actually going to start today with some history, kind of like I did in one of our chemistry lessons. We're going to talk about some theories that physicists have had in the past. And one of them, this was actually Aristotle. I'm pretty sure I gave this to you in a previous set of notes. Aristotle. Aristotle had this concept. He thought that everything in the universe was made of 4 elements: earth, wind, fire, and water. You guys remember talking about this at one point before? Aristotle? He was very wrong. The elements are things like copper and hydrogen and helium, not earth and air and fire. And like, not only was he wrong, but like he was really wrong. Fire is not even matter. Fire is better described as energy. Okay? And so early physicists, they were really struggling to try to like describe how these things worked with each other. I have a little note here. You guys can read this. It says that objects, they thought that objects contained fire. I'm going to put the word contain in quotations. They thought that certain objects had fire inside of them, and somehow it just burst outward. For example, like a log, a piece of wood. A piece of wood, they thought that wood had fire buried deep inside of it. And if you lit a match and got it going, all of a sudden then the fire could be released. You know what I'm saying there? And like, we now know that that's not really what's happening. What's really happening is that chemical bonds are being broken and formed, and like an exothermic reaction is taking place. But yeah, they used to think that like certain things had like a magical internal fire inside it. We have a name for that. We don't use this name anymore because it was totally wrong, but they called it phlogiston. You ever heard that word before? And basically the idea is that there was like certain things like wood had phlogiston inside of it. And therefore, when you lit it on fire, it could escape. Right? But if you tried to light a piece of metal on fire, some pieces of metal don't light on fire, and so they would say that there was no phlogiston inside of it. And like here, the ashes, their logic was the ash for the wood, it had no phlogiston, because where did the phlogiston go? Well, it went into the air. Okay? They were very wrong. But it's kind of worth talking about what their previous theories were. Okay? They had a similar theory for heat, actually. They called it caloric. We actually still use this word to this day, only we talk about it like with calories. But like calories for food are really a measure of energy. They were kind of getting closer to being on the right track, and they thought that heat was this substance that everything had, and that heat flew from warmer to cooler things. It wasn't until the year somewhere in the 1780s that a scientist, he would have been a noble because he was a count, he had this brainstorm, this grand idea. And I want to present the idea to you here. They made a cannon. Okay. And like in my mind, I think of like Johnny Depp in Pirates of the Caribbean, where they're like shooting at each other with cannons on ships, right? How do you make a cannon? Well, you have a big piece of metal, and yes, you put a ball inside of it, but there has to be a hole inside this big piece of metal. How do you get a hole inside this metal? You have to bore a hole with tools. And if any of you guys have worked in the metal workshop before, you're literally grinding out the metal. Right? What happens when you grind out metal? What happens to it? It becomes really hot due to friction. Yeah. Now, we know about friction now. But back then, they didn't even get that concept. And so this was very confusing to them, because what they were doing is they were grinding a hole in the cannon, and they had metal. And they knew that metal didn't have caloric or phlogiston, because if you try to light the metal on fire, does it light on fire? And big yawn there. And the tool, like the lathe, the drill bit, right? Think of it as a drill bit, right? The drill bit also didn't have any of that caloric inside of it. And yet, when you drilled the hole inside, it became really warm. And that was perplexing, hence this question here. What was the source of the caloric? How did all of a sudden two objects that didn't have phlogiston caloric, magical inside energy, how did it all of a sudden show up? And I mean, it sounds kind of weird to us because I think you guys even get this already. But back in 1780, they didn't know what they were talking about. What we now know is that mechanical energy in the form of friction is what was turning into heat. The actual act of like moving this lathe around and drilling the hole in the cannon, that was what was giving us the heat. We know that now, right? Because I even heard one of you guys say friction, right? So, but I want you to put yourselves in their time frame. They didn't know about this yet. Fast forward 60 years. A guy named James Joule was trying to figure out how to quantify heat. Okay. We've discussed a couple of words, hopefully. One of them is the word quantitative. Do you guys remember the word quantitative? It means there's a number associated with it, right? And so previous to this, let's say there was a fire, and it was a big fire. Well, you could say that it was a big fire, but you could put a number to it, right? Let's say it was like a little fire. They had no way to like put a number to it. That's what James Joule was trying to do, is figure out, how do I associate a number with heat? And this is a very crude experiment, but it worked quite well. The picture itself might make sense. Here's what he did. He had a beaker of water, put a thermometer inside. They had thermometers. Okay, those existed. I'm going to point one thing out, actually. What does a thermometer measure? That's not heat. Temperature is not heat. Okay? Temperature is a way that we kind of utilize collectively to measure heat, but there is a difference there. Okay? Heat is a form of energy. So although they are related, I need to point that out, is that the units for temperature are in degrees Celsius. And what I want to show you here, actually, is that energy. Does anybody know the units for energy? It's joules. Yeah, it's joules. Fahrenheit is actually another measure for temperature. Okay? Temperature and energy are related. They are different, however. Okay? We actually named the unit of energy in honor of James Joule. It's a capital J. Okay. Anyone ever heard of like you use like a kilojoule of energy or something like that? That's energy. Okay. Anyways, here's the picture. What it is, he set up a weight on a pulley system. The weight is naturally going to fall, right? As the weight falls, it causes this thing to spin around. And as the spinner spins, it creates friction. And as it creates friction, it heats up. And we can measure that heat using a thermometer. Does that make sense? And so what he did is he might have put a 10-pound weight on first. And as the 10-pound weight fell, it caused it to spin a certain amount, and it heated up maybe like, say, 2 degrees Celsius. Then he puts on a 20-pound weight, and it falls with a little bit more force behind it. Right? And that causes it to spin with a little bit more torque, and maybe then it raises 4 degrees Celsius. You kind of get how this experiment worked? And this was the first way that a scientist tried to find a way to put numbers to things. Okay. Now, I do need to point out, though, that these numbers are temperature numbers, and they're not the same thing as energy. There's a conversion formula, which we're going to learn at one point. But, yeah, he found a way to basically quantify energy. So what I want to talk about now is some of our current theories of energy. And I put a picture there of somebody who's totally passed out and tired from like studying or something. When we discuss energy in the real world, we often refer to it as having like mental or physical stamina. Like, for example, if you're about to go play a football game, and you'd say before, I need to have a lot of energy to go play my game. That's usually how we describe energy, where it's like, oh, I'm so tired, I have no energy today. Okay. That's how we use the word, but like that's not the scientific definition of the word. Scientifically, there's actually no good definition for energy. Maybe that sounds really dumb, but like if you asked me, Chris, what is energy? I would have a hard time describing it. Because it's a very abstract concept. Like, how do you discuss something that isn't a thing? Right? Like, matter is a thing. I can describe this desk. I can say that it's made of wood and metal and it's blue and it's silver, right? Like, I can describe matter very easily. But energy is different. Energy is like how we move the matter, okay? And so we don't actually have a good definition for energy. The best one we have is this. Energy allows you to perform work. And by work, I mean like do stuff. Would be the best way of putting that. Okay? If you have energy, you're capable of doing stuff. Now, in the real world example, if you have energy, you can go and do your job, you can do your homework, you can play football, right? But in a physics concept, if I go back here, if I have energy, the energy allows stuff to happen. What happened in this picture? What is the stuff that occurred? Motion is the stuff that happened. Right? The energy that I had caused the weight to fall. That caused this thing to spin. That caused this thing to spin. It caused like motion to occur. Does that make sense? So often energy is highly related with motion. But that is not the only form of energy we have. There's actually lots of different forms. And that's what this next little bullet talks about, is that energy has many different forms. Let me give you some other examples, and I've got slides coming on later. But light is a form of energy. Heat is a form of energy. There's nuclear energy. There is potential energy, like in a battery. So that's what I've got some slides on talking about here. But what I need you guys to know is that energy always allows you to like do something, whatever that something is. Okay. Originally, the Greek word for energy was the word energos, meaning active. That's why I wanted to use the word motion. If something is able to move, that probably means there's energy involved. Okay. Is there a lot of energy happening on my front black table there right now? Not really. Nothing's really moving. Foosball table. A lot of energy going on there. I throw something? Yeah. Right? Okay. So let's talk about a few forms of energy I want you guys to know. Here's the first one. They were very wrong about this whole phlogiston caloric concept. They thought that like buried deep inside of wood was this magical fire trying to escape. They were wrong. What we now know is that it's actually chemical energy. That's one form of energy. Chemicals have energy involved. And you guys should know these words because we talked about them. The words exothermic and endothermic. All reactions either require some energy or give off energy, right? And it all has to do with bonds. Inside the bonds of your chemicals, those either require or give back energy as they're broken up. And so we now know that it was actually the bonds that provided the energy for the fire to go, not some sort of magical caloric. So that's one form of energy, chemical energy. Maybe the best example of chemical energy I can give you is a battery. A battery is chemical energy. It's stored inside the bonds of the materials inside the battery, and as the battery runs, it uses up that energy. Okay, here's a couple more forms of energy. Electricity and magnetism. They're actually highly related. They're both forms of energy. When you're running your stove or your microwave or your Xbox, I don't really know, right? Whatever. That's a form of energy, electricity. Okay? And magnets are another form of electricity or another form of energy. And Thomas Edison actually was able to prove how he was able to combine these things. For example, a light bulb takes electricity and makes light and heat. Right? Isn't that the point of a light bulb? Right? Take electricity, and I mean, you're supposed to make mostly light, but it does make heat as well. What we've been able to prove is that like different forms of energy, they can transfer from one to another. Okay? It's actually possible to take a moving magnet and a coil of wire and make electricity. We actually have a name for this. We call it a generator. Generator. If you take a magnet and a coil of wire, you can actually produce electricity. So those are some more forms of energy. Say that again. I still missed whatever that first word was. Say it one more time. Oh, oven. Yeah, oven would be a good example, right? It's producing heat and light. Sorry, I missed oven. That was the word I didn't catch. Yeah, I'd agree. Yeah. Okay, here's a couple more forms of energy. Nuclear energy and solar energy. You guys are probably familiar with solar energy, right? We get our energy from the sun. It's light, right? And heat. Right? Nuclear energy, back in the turn of the century, the 20th century, 1896, this guy, Henri Becquerel, he discovered that you could actually make nuclear energy. Now, we've now harnessed this to make nuclear reactors and nuclear bombs. There's actually two different types. There's fission and fusion. Basically, the way it works is that if you take a nucleus of an atom and a second nucleus of an atom, and you find a way to shove them together with so much force and impact that it can actually make a fission, or that's a fusion bomb. Sorry, fusion is where two atoms combine. This is actually what our sun does. Our sun takes a hydrogen 2-1 molecule and a second hydrogen 2-1 molecule, and it turns it into helium 4-2. And that is fusion. And it produces a massive amount of energy. Atomic bombs actually work under that same process. Fission is where it breaks up into pieces. The most common example of fission is uranium-237. Uranium-237 is, I believe it's 92 protons. And what it does is it breaks into two pieces. The big, big, big nucleus that has all of these different pieces inside of it, it cuts in half and they split apart. And if you can split an atom, that's called fission. So, I don't need you to know much more than that. I just want you guys to know that those are forms of energy as well. Okay. And here's some more. Here's an even bigger list. Thermal energy. What do we actually call thermal energy, though? Yeah, heat. Right? Chemical energy, electricity, radiant energy. That's energy that comes in the form of radiation. Yeah. Right? Nuclear energy. Often these two things go together. Often nuclear energy leads to radiation. There's energy in magnets. What about just an elastic band, right? You take an elastic band and you want to fling it at your friend, there's energy there. Sound is a form of energy we often kind of ignore. I want to talk about this word for a bit here. Mechanical energy. Mechanical energy is the sum of all energy. It's not the best definition I have, but it'll work. Let me give you an example. The light above us. The light is producing mechanical energy, and it's really producing three things. It's producing light, it's probably producing heat, and it's probably also producing sound. Does that make sense? And if I were to, yeah, because can you sometimes hear the lights buzz a little bit? That's the projector, I guess, right? You ever heard a light bulb have a little like a to it, right? Okay. If I were to add up all of the collective energy, the word we use for that is mechanical energy. Okay. So for example, if I was throwing a flashlight, okay, it would have energy due to its light, but it would also have energy due to its motion as well. Okay. So mechanical energy basically means that add up all the energy that you have. Okay. Luminous energy is light. And this last one right here probably won't make a lot of sense, but have you guys ever heard of the formula E equals mc squared? You're probably not overly ready to learn this yet because that's physics 30, but there is a relationship between energy and mass. We can actually use mass to create energy and vice versa, but that's a big concept. So, but these are all forms of energy, and they can transfer from one to the other. For example, electricity can provide sound and light. Right? Or for example, nuclear energy can cause radiation to occur. So I need you guys to know that all these things can transfer from one form to the other. Okay. There's one more on here that I didn't give. I want you to write this one down. It's called kinetic energy. And the best way of me describing kinetic energy is it's the energy of things that are in motion. All the rest of these things right here are energies that are there's no matter necessarily happening. Like heat, for example. Let's say there's a fire going on. The heat itself is not matter. Okay? And there's sound itself. Sound does not matter. Okay? But kinetic energy is the energy of things that are in motion. So if I were to throw something, it has kinetic energy. Does that make sense? Yeah. We're going to talk about force. In order for things to get energy, forces have to occur. So, okay, that's my lesson for the day. It's a really basic thing. I mean, honestly, I can't even give you an assignment yet, because we didn't really learn a whole lot. We're working our way in. So we have 20 minutes left. So in a few seconds here, I'll let you guys scatter to other places if you want. But let's do a quick recap of the lesson and then of what I want you to do. Today's lesson was a little bit of history. Not a lot, but we talked about what physics is all about. Physics is all about what gets stuff doing things. Matter is our stuff that we talked about in chemistry. And physics is what makes our stuff move and do things, right? What is light? What is sound? What is heat? Okay. So we talked about a lot of different forms of energy. And we talked about two really important scientists I want you to know about. Okay. First one was Count Rumsford. It's really, really simple thought, but it was the first time that someone realized that like two cold objects could produce heat when they were like rubbed together. He kind of like figured out that this whole caloric thing was way wrong. And then I want you to know the name James Joule, okay? Because he was the first guy who kind of realized I can find a way to attach a number to it. We're not doing any math today, but we will soon, okay? Bring a calculator tomorrow because we're going to do a lot of quantitative calculations where we do a lot of algebra and math, okay? Okay, so that's today. Quick recap then of what to work on otherwise, okay? If you are done everything and you are content on that learning cycle there, if I've taught you stuff, you've done it, I've given you feedback, if you want to be done, give me a progress log of what you've got. Okay. But I'm more than okay with you guys redoing tasks, submitting them again. For anyone who hasn't handed them in the first time, ask me to look at it before you hand it in, okay? Many of the labs, I wouldn't say they were poorly done, but I think people didn't know what I was expecting, perhaps. So I'd like to kind of walk you through what I was expecting to see so that you can do a better job of it. So take this last half hour and kind of start working on getting your chemistry finished. Sound good? And if you want to, go work somewhere else. The one piece of advice I want to give you guys this unit, when I come around and I ask you, can I help? Don't say no. Say, yes, Chris, mark this for me. Tell me whether I have it right, okay? I mean, I'll move on if you want me to. I'm not going to, like, badger you that much. But, like, take me up on my offer. I will mark things for you. I will give you advice. That's why I have a job. All right, sound good? Okay, feel free to scatter if you want, or stick around and ask me questions.